Hello everyone, welcome back to DDL's PackReview series. My name is Peter Johnson. I'm here today with Scott Levy, and today we're going to talk to you a little bit about accelerated aging, particularly based off the ASTM-F1980 standard. Scott, can you speak a little bit about relative humidity and how that plays into the accelerated aging?
Absolutely. It's probably one of the key questions that I get asked on a regular basis. What relative humidity should I utilize for my accelerated aging? And what everybody needs to understand is accelerated aging is all about time and temperature. Humidity really doesn't play a role in that Q10 factor. It's simply time and temperature. But at the same token, especially in the medical device industry, everybody wants their tolerances at plus or minus 2, plus or minus 5, etc. So what humidity should I utilize? Well, what we understand about packaging materials and relative humidity is you want to age your stuff at a low relative humidity. Why? All right, at 23C, 50% relative humidity, that's ambient, right? As you elevate the temperature for accelerated aging, 50, 55, 60, whatever the test temperature is, you're trying to mimic that same amount of absolute moisture content as 23C 50. And if you start looking at the psychometric chart in ASTM-F1980, it kind of shows you what relative humidities you should be looking at if you should so choose to use it. So for example, at 55C, I think the standard talks about 7%. Okay? Now 7% is a very low RH. Typically DDL as a whole, we go less than 20%. On average, we're sitting about 9 to 10%. But the key thing to keep in mind is you want as low as absolute possible. If you elevate your relative humidity with an elevated test temperature, let's say you're at 55 at 60% relative humidity, and if you look at the parts per million or the absolute moisture content, you're probably over 100% saturation rate. Why is that a problem? Well, the problem with that is if you have a failure in accelerated aging, or the testing you do after accelerated aging, is that realistic to what happens in the real world? Well, absolutely not. First, you need to understand that in the real world, you're not aging your samples at 50, 55, or 60C. So you want to make sure that you're choosing a relative humidity that's going to work properly for your specific test temperature, and that you do not go over the threshold points where basically it's going to rain on your samples. You do not want to cause a failure that you're never going to see in real-time aging.
So once the accelerated aging is done, what happens next?
Well, I think that's another big misconception, that if you run accelerated aging, you get your expiration date, and that's not the truth. Accelerated aging is simply a conditioning step. It doesn't tell you whether you pass or fail. It's what you do afterwards that's going to tell you whether you pass or fail. So for package validation after accelerated aging, you're going to execute your physical strength testing, your physical integrity testing to prove out that no adverse effects from aging has caused a sterility breach in the package. On the flip side, if it's product testing, well then you're going to take your product and go through your whole battery of tests that you would have done at T0 or your baseline to ensure that aging hasn't caused adverse effects, and then compare those results back up.
So Scott, tell me a little bit more about real-time. Why is that important?
Well, real-time aging is critical. Again, you're allowed to use accelerated aging to get your product to market. So think of it this way. If you have a brand new medical device and you have to let that device sit on the shelf for a 3-year expiration date, by the time 3 years comes due, it's going to be obsolete, right? So again, accelerated aging is a gift given by the medical device, or given to the medical device manufacturers by the FDA and governing bodies to allow people to bring their products to market. But the critical aspect with any type of aging is your real time, because that's the definitive data that you're going to get from having your sample stored on the shelf for the same specific expiration date that you're using for your accelerated aging.
So can you take some of the real-time samples and then accelerated aging?
Sure. If, let's say, arbitrarily, I have 120 samples sitting on the shelf and they're coming due for a 1-year expiration date, okay? Could I then take half of those and then put those into accelerated aging to gain another year of expiration? Sure, you can do that.
So Scott, help me out with the ambient temperature and how that's used in the accelerated aging calculation.
Sure. With the accelerated aging calculation, you have to pick your elevated temperature that you want to age your samples at, all right? And then, per that calculation, they want to know what ambient temperature you'd like to use as well. So let's say I'm using a test temperature of 55°C, okay? What's my ambient temperature? The ambient temperature is directly related to where you're storing your real-time samples at and what ambient temperature that is. Is it 20? Is it 22? Is it 23? Is it 25? Whatever and wherever you're storing your samples, that temperature is what you should be using for your accelerated aging calculation. I get a lot of questions regarding, so if I use an ambient of 25, doesn't that push the total number of days out? Well, sure it does. So I see a lot of customers playing the game of, all right, we really truly store our stuff at 25°C, but if I use an ambient of 20°C for the aging calculation, it shortens the number of days. But ambient temperature in general is specifically related to what test temperature you use for real-time aging.
What are some of the biggest issues you see with accelerated aging?
I think the biggest issue is the medical device manufacturer not allowing enough time to do it properly. What do I mean by that? All right, well, you need a 5-year expiration date. I just had a call like this. I need a 5-year expiration date before next month. And I'm like, there's no physical way to do this. Even if you move the temperature to 100°C, you know? And that's what a lot of people will look at. They'll look at that Arrhenius equation and keep moving that test temperature up to suit their specific needs for when their launch date is. But putting those samples again over 60°C is causing a lot of red flags to come up for regulatory once in review, and problems with their product performance as well as their packaging systems failed by choosing a test temperature that's not going to realistic mimic the specific materials that they have without catastrophic problems. So planning is probably the biggest number one issue I see immediately. If I have somebody call and say, you know what, I want to run something at 70°C, the first question out of my mouth is, you need this quickly. And typically that answer is yes, we need this data very fast. Well, what are you doing with that data? And if it's for a submission, then we'll go back through all of the aspects I've talked about earlier about how you get questioned on using this high of a test temperature when the standard counsels you not to go over 60 or take risk in going over 60. You got to have a pretty good justification. So that's probably the biggest pitfall I run into. How about yourself?
Well, with the accelerated aging and my customers, like the standard suggests, not to go above 60 unless you are able to have written documentation on how those materials react.
Yep.
So I counsel all my customers on staying at 60 or below unless they have data support otherwise. Thanks everyone for joining in. As a reminder, you can visit our website for more PackReview series at www.testedimproving.com.